Hello everyone, today I'm going to try to review a small power adapter bought from Dinodirect.com. It's one with a USB jack and it's supposed to deliver up to 5 volts 500 milliamps of power. It's only $1.67 US dollars, so it's going to be fun to see how much it can actually deliver and how good the quality it is inside. So for that I'm going to cut out the jack on this USB cable to make it easy to measure the voltage and the current. I'm going to use a power meter which is capable of showing how much power it draws from the mains, a multimeter to show the voltage. Well, actually it's gonna be this one. Sorry about the brightness because it's a new camera and I'm not yet an expert with it. And this meter is going to be measuring the current I'm going to draw from the power adapter. This meter is pretty accurate. For example, let's see if I connect this computer to it. We'll see how much power it actually draws from the mains. So as you can see, even turned off, it draws 3.8 watts from the mains, standby power. So it's pretty accurate. Okay, the cable is cut. You can see the red and black wire. Red is 5 volts, black is ground. I've tied a solid wire, a solid orange wire as a ground, and the white and orange wire is the 5 volts. This makes it easier for me to connect the multimeters to the wire and the scope to see how good the quality of the output is. Let's connect the multimeters and plug this in. Well, let's plug this in right now, it's easier. So you can see the green LED lights up, and even without anything connected to it, it's drawing 0.2 watts from the mains. Let's see how good the voltage on the output is. Okay, we have the multimeter connected to the input. It shows 5.66 volts without anything connected to the adapter. I suspect there's a Zener diode, a 5.6 volts Zener diode inside that blocks the voltage when it goes above 5.6. And we have the scope connected, and you can see the quality of the output voltage up to 0.5 volts ripple at as usual very bad quality. So let's start our current load and see when there's something connected to it how well it works. Power up. Okay, we have to connect the load to our adapter. Okay, our constant current load is connected to the adapter. Right now 0 amps, yet just with it connected the adapter is pulling 6.6 watts from it. So let's increase the current. (25 milliamps), 6.9, and still 5.6 volts, and still poor quality. Let's go up. I'm going to put the camera down because it's easier this way. There we go. So we're up to 100 milliamps, about that much. Milliamps, still 5.6 volts, 7.4 watts at the mains, so very poor efficiency and still bad, a lot of ripple and bad quality. Let's increase even more. (200 milliamps), it finally goes down a bit to 5.58, 8.5 watts at the mains, and let's go up. So at 300 milliamps we have 5.53 volts and 9.4 watts at the mains. At 380 milliamps we finally have 5.2, so it's starting to get closer to 5 volts, and we have 9.9 watts from the wall. And I'm going to change the scope scale. So you can see how it starts to suck even more. 1.22 volts ripple. So the adapter already can handle quite okay this load of 360 milliamps, 380 milliamps. So let's go up to 500 now. Okay, so actually at 400 milliamps, 420 milliamps, the output voltage is already 3.8 volts, and that's the quality of the output. It goes between 3.1 and 4.2 volts. Because I suspect the output capacitor is too small, and also probably, well, we'll see how the insides are made. And interesting, the adapter now has the LED red. Let's see if we go back, if it goes green again. (200 milliamps), it's still red. And now it's green, so let's see where. Okay, so it changes to red just at about 100 milliamps. 100 and it's red and green. 150 and it's red. So let's go to the max, to the 500 milliamps. It's about 510 milliamps here actually, not quite 500. And we have 1 volt at the output. It's not capable of doing 500 milliamps. Let's see, let's go down. And that's about pretty much what it can do. At 390 milliamps, you could say it's still a 5 volt adapter. 4.6 is still within, it's at the limit of the lowest limit of what a 5 volt adapter should be. So this adapter is actually capable of 400 milliamps, let's say 400 maximum, but really you shouldn't use it for more than, I don't know, 300. Yes, at 300 milliamps is still 5.4 volts. So let's open it and see what's inside. It's fairly easy to open, just a screw at the bottom here. Okay, so let's open it up. Oh, the brightness is really horrible. So let's go step by step. Oh, well, look at that. The AC wire just disconnected from pulling it out. Poor quality. Okay. So AC voltage goes in, goes through a single diode and goes halfway rectified. We have a small, probably, yes, a 2.2 microfarad capacitor, goes through a very small transistor, Let's see if night shot works better. (13,001) transistor goes through the transformer. At least there's a output optical isolator, and there's probably a small secondary coil that provides feedback to the main transistor, so it can actually get feedback and try to keep the voltage within limits. So as I suspected, I guess that's the Zener diode. The Zener diode that clamps the voltage to 5.6 volts, so it doesn't go up to 10 or more. Interesting. And let's see the back side. No fuse. Yes, no fuse, at least that's at the top, no fuse. And there's no capacitor to connect the secondary side to the primary side for EMI suppression. And let's look at the back side. And you can see it actually has a PCB fuse, a very thin trace. If the current is too much, that PCB trace is supposed to break. And the separation between the primary and the secondary is not that bad, but also not very good. Not as large as it should be, but you could say it's acceptable. Oh well, so how could we improve it, and why? Well, this sucks mainly because it's halfway rectified. It's just one diode at the input. And let's see the output capacitor, how good it is. It's really bad lighting here, I apologize. Yes, it's a 220 microfarad 10 volts capacitor. Yeah, right. Okay, the mains cable is back soldered into place, and I should correct myself and say that the adapter is actually not drawing 6.6 it's not drawing 8.5, 9.4, 9.9, 10 watts at the max, but it's actually drawing 6.6 watts less, because 6.7, 6.6 watts was actually the power supply that was powering my constant current load. I forgot that I had it connected to the same power source, which goes through the power meter. So it actually draws about 3.5 watts, no, sorry, 2.1 watts, 3.4 watts, and so on. So it's probably about 70% efficient. Not that it matters, because if it can only deliver 380 milliamps, 400 milliamps at 5 volts, and then it goes down to 4.6 and much lower, it becomes useless at more than 400 milliamps. So let's see why I suspect this can do more. Well, I suspect it's mainly because of very undersized input capacitor, and because it's a halfway rectified. For those that don't know what that means, well, basically at the mains you have AC voltage, which looks like this. In our country it's 50 Hz, so that means 50 times a second the voltage goes from a positive voltage to minus 200 whatever, 230 volts. So 50 times a second it oscillates like this. Well, this adapter works with DC voltage, so the voltage is supposed to be like a line like this. So what the half wave rectification does is to add a diode which basically cuts all these peaks below, and you're only left with these pulses at the top side, positive voltage. And then a capacitor is used to store a bit of energy between these pulses of power, so that you won't have 0 volts in these moments. So this 2.2 microfarad capacitor is supposed to work kind of like this. When the pulse goes up, the capacitor charges and keeps energy that to fill like this, the empty space. Then when the input goes up again, capacitor charges to the maximum again, and repeats the process. So you get a somewhat of a straight line, but with lots of it goes down a lot. Well, ideally with a large enough capacitor you can have a pretty straight line, but with this 2.2 microfarad capacitor I suspect that the energy in the capacitor at 400 to 500 milliamps it's only enough to keep it straight for pretty much to about here, and then the capacitor is discharged, and now you have an empty space here, and basically the adapter stops working because it has no input power. Then we have again input power from the mains, capacitor charges, and the adapter starts working again. So for a very short moment, about, let's say, this length is about 20 milliseconds, I think, or 10. For about, let's say, for about 5 milliseconds, the adapter is completely stopped. So how come it keeps working and delivers output voltage with a lot of up and downs? Well, it's the output capacitor, which 220 microfarad. This one also charges when the peaks are up and the adapter works. The output capacitor charges up, and it manages to keep the 5 volt. It manages to store energy enough to provide up to 400 milliamps relatively well, but at more than 400 milliamps the adapter stops working properly. It goes to, as you saw, it goes to 3.5 and below. Let's see. Well, actually it's not plugged in now, I can't test again, but you can go back in the video and see how it sucks. So how could we improve it? We could try to improve it by increasing the output capacitor from 220 to, let's say, 470 or 1000, and that's also going to provide a somewhat better output voltage, more stable output voltage. But really I suppose it would be better to also change the input capacitor to a somewhat bigger size, just to see if the efficiency or if it actually works better. So I'm going to put the camera down and first of all change the output capacitor to, let's say, 1000 microfarads, and see how it changes, how the output changes, and if it can do more than 400 milliamps. And after that, if it still sucks, I'm going to change the input capacitor and maybe I'm going to also try to use a full bridge rectifier instead of that single diode on the input. So I'm going to make it a full bridge rectifier, which basically means that instead of just chopping these parts, the full bridge rectifier actually inverts these and makes the output voltage like this. So now the input capacitor doesn't have to provide energy for this whole empty space like in the half bridge rectifier. It only has to have enough charge to fill up this gap, this small gap of about less than 1 millisecond. So even 2.2 microfarad should be enough to fill up this small gap, these small gaps. But I think I have a 4.7 or a 3.3 microfarad capacitor, so we'll see how doubling up the input capacitor changes things. Well, I went through my boxes of capacitors and it looks like 1000 microfarads is a bit too much because it won't fit inside the box if I use 1000. So I'm going to use, even though I don't like it, I'm going to use 820 microfarad. Oh my god, the lightning sucks here a lot. .820 microfarad, 6.3 volts, and I'm going to connect it somewhat sideways so that it will fit inside the case. It's 6.3 volts. I'm a bit concerned, but it's a quality capacitor and the voltage is clamped down to 5.6, so I suppose it will be safe. I don't like it too much, but I'm not going to use this adapter anyway. It's too shitty for me. I don't like it at all anyway. It's just to play around with it and test. Okay, let's go back and put the camera down, solder it in place, and let's test. Okay, the new capacitor is in place. 820 microfarad, 6.3 volts. It sucks, but like I said, I'm not gonna use this in regular each day. And just for kicks, let's measure this capacitor and see what it actually does. It's really small. It's really small to be... Oh my god, the lightning really sucks here, I'm sorry. So I really don't think it's 220 microfarad, 10 volts. It's kind of small to be like this. So I'll measure the ESR and the capacitance. Okay. You should see that value. Okay. Well, it's 210 microfarad, 0.28 ohm ESR. So I placed the 820 microfarad, 0.05 0.06 ohm ESR instead. Let's see what happens now when I plug it in. Of course I'll have to be very careful when I plug it in because I'm not gonna put it back in the case. So actually I think I'm gonna put it in the case because nothing prevents me from doing it. It still fits. One moment. Here we go, it fits right in, no problem. Check that the leads don't touch. Okay. And the cable. Oh shit. Okay, good enough. Okay, we have the scope back. So we're at 160 milliamps. Pretty stable output. Yes, let's go up. Three 300 milliamps, still 5.67, 5.51 volts, still pretty smooth. About 360 millivolts ripple peak to peak, 400, which is pretty good. Let's go up to 380, which was our previous limit. 350 milliamps. We still have 5.46, but you can see it's starting to oscillate and go bad. 480 millivolt. 0.5, 520 millivolts ripple. It starts to go bad, and let's go slowly up. And at 300 and about 400 milliamps we have 475 volts, and it's about 687 20 millivolt ripple. So the output capacitor is a small improvement, but not by much. Let's see, it was about 4.6 the cutoff value before, and it's about the same now. Let's see how much we can go until it goes way bad. Okay, at 425, 440 milliamps we already have 3.3 volts, which is horrible. So not much of an improvement. Still 400 milliamps, even with a 820 microfarad output capacitor. So the next step is maybe to increase the input capacitor from 2.2 to a better value. I think I have a capacitor here. Yes, this one is a 4.7 400 volt, and the one inside is supposed to be 2.2 400 volts. So we'll see if doubling up the capacity on the input will help a lot. Let me take down the load. Okay, so I'm going to replace this with this capacitor, the input capacitor inside. Okay, a new capacitor in place, and just for kicks I'm going to test this 2.2 microfarad capacitor on the ESR meter. So as you can see, 2.4 microfarad, 11 ohm ESR. So this new capacitor I have in place, it's 4.7 microfarad and about 5 ohm ESR. So it should heat up less, theoretically. Okay, let's put it back together and see what happens. Okay, new capacitor in place, input 4.7, 4.4, 4.7 microfarad. Okay, no load, 5.6 volts like before. Well, actually it's a 50 milliamp load, but whatever. Okay, let's increase the load slowly. $100 milliamps, 5.6 volts, everything okay. Let's go up to 250. 250 milliamps, still okay, 5.5 volts. 320, 200 millivolts ripple. It's a bit better, I think, but I'm not sure. Let's go up to 300. Still 5.5. Still acceptable ripple. Peak to peak 360. And let's go up to 380, where it starts to suck. It started to go bad before. So 380 milliamps where it went bad before. It's now still 5.4 volts, and the output is just a bit going bad at 440 millivolts. Okay, so let's go up again. 10 watts minus 6.6 watts the power supply. It's 4 watts used to generate 400 milliamps at 5 volts. That's about 2 watts. So it's about 50% efficiency at this point. So let's go up to 400. 430 volt milliamp. It's 4.1 volts, but at least it's relatively stable, unlike before where it was really a wave, ugly wave. Okay, so let's go back a bit. 420, about 420, 4.3 volts, still too bad. Okay. Okay, so even with the input capacitor of 4.4, it's still just 400 milliamps. It just goes down straight from 5.1 volt at 395, 400 milliamps. It goes down quite fast. So let's see what happens if I put a bridge rectifier instead of that single diode. Let's see if things improve much more. It may be possible. It may be that the 4.4 microfarad it's still not quite enough to keep up with these big drops of power when it's halfway rectified, when the mains voltage is halfway rectified. So let's experiment. Okay, I went through my box of parts, and apparently the only bridge rectifiers I have are some seriously oversized bridge rectifiers. This one is a GBU 405. It's a 4 amp 600 volt bridge rectifier. This adapter only draws about 0.1 amps, 0.2 amps from the mains, but this one will work just the same. I just have to solder 4 wires to it and MacGyver this bridge rectifier inside the adapter. Well, outside, because it won't fit inside. I just have to be very careful with the mains voltage and to insulate the center pins, actually all 4 pins, because it's still 350 volts about when it's full bridge rectified. Okay, the bridge rectifier is in place. I've connected it to the mains with the green wires. They go in the center, and the orange and white orange are the DC negative and positive. I've pulled out the diode and connected it directly on the traces. So I now have to be very careful, because this is going to be the wires are not 230 volts rated, so the insulation may melt soon, so I can only keep it running for a shorter period of time. Connect the USB cable. Have it stay on paper because it's insulator. I've turned off the socket, but it may still be neutral connected, so I'm not taking my chances. Oh god, this it's protected for kids and it's very hard to plug in. There you go. No, it won't stay in. It's so bad it doesn't stay in. Well, we'll see what happens. There we go. Hopefully. Okay. Let me put that bridge rectifier on some paper to insulate it from the desk. Okay, check for shorts. Okay, they're separated. The constant current load is separated. And let's turn it on and see if something blows up. No, all okay. Straight to 400 milliamps. Load. Okay, go back to 0. And let's see if that changed anything. I'm gonna put the camera down. Actually, it's better in my hand. And let's go up again. $100 milliamps. .5 volts. about the same. $300 milliamps, 5.3, 400 millivolt peak to peak. And now let's see if the full wave rectifier improved things. 350 milliamps, 5.3 volts, still 400 millivolt ripple, $400 milliamps, 5.2 volt, and still 400 millivolt, 520 millivolt ripple. Okay, so it looks like it goes a bit higher with a full bridge rectifier. Let's try even more. 440 milliamps, and it goes down to 3.8. So just about 425 milliamps, it's the best we can do with, even with a full bridge rectifier, a bigger capacitor on the input, on the output. It's really, I guess the transformer is undersized for the job, probably. And one last thing I will do before I finish this video is to use one of these things to measure the temperature on various parts of the transformer. Is 45 degrees, output capacitor 40, 38 on the 33 on the input capacitor, transistors 40. So the transformer is pretty much the warmest part at 46, but I let it run for about 5 minutes before, and it went up to about 55 degrees. So you can imagine if it sits in a big in the small case, if it's tied inside, if it's sealed in that small box, what will happen if you charge your device for about 2 hours, 1 hour, and the device pulls about 400 milliamps as it does right now for about 1 hour. You can imagine how hot it will be inside. So that in turn weakens the capacitors. In time they go bad, they dry out. So conclusions, it's a very cheap adapter. It's crap, you can throw it away. It's not able to do 500 milliamps as it says on the label, no matter how hard you try. As you can see, I even tried to use a bridge rectifier. I increased the output capacity, I increased the input capacitor in order to try to improve this adapter. It's just not capable of doing more than 400 sorry about that. It's not capable of doing more than 400 milliamps before it goes bad. So even at 390, 380 milliamps, it's capable of 5.3 volts, but as soon as you go above 400 milliamps, it goes bad. So I don't know, maybe a small MP3 player, some stuff that draws up to 250 milliamps, it may be okay, but over 250, 300, it shouldn't be used. well, actually you shouldn't use it at all, because it's really cheap and bad. I actually just ordered it as a basket filler to get a discount on other stuff, to go above a certain value for the whole package. That's why I bought it. I knew it was crap from the start, but it was fun to test it, even though it took a while. Okay, that's about. Let's measure the temperature again and finish this video. So as you can see, just talking, the transformer is already at 53 degrees. 50. It just went up 5 degrees as I talked for 2 minutes. Well, that's all. Again, I really apologize for the bad lighting. The sun, I had to put the shades because the sun was very hard, making it very hard to see the scope. And this small lamp is really small and weak. I have to get some better lighting in this room. Okay, thank you for watching.